This particular way of doing interacting problem is what is known as configuration interaction. Again, many of you might have heard this acronym called CI. So, this is actually called the configuration interaction. In fact, this is done much after Hartree-Fock normally. See, first read Hartree-Fock, which is only one electron, one determinant, and then you go to this. But this is potentially much simpler to explain because it is very simple mathematics. So, you just, what is configuration? Configuration is determinant. Interaction is a combination. So, that is why it is called a linear combination of determinants or linear combination of configurations, and this is called the configuration interaction, and very popular quantum chemistry method called CI. Now, depending on how I truncate, of course, nobody can do all. The CI has different flavors, CISD, CISD triples, all that we will do later. The point is that mathematically this is an exact form, provided my basis is complete. So, the question that she was asking, the basis is not complete, of course, you are right. So, this was an example, but if I take that 3 to be a complete set, potentially this is an exact, or 4 to be the complete set, potentially it was an exact. So, if I have a complete basis, that is one, and within this complete basis all determinants, remember my basis may be complete, but I may choose that I am not going to take all determinants, I am going to only remove some determinants. So, that choice is also there. So, there are two levels of approximation, one is the basis, one is the number of determinants. I need not take MCN, even if M is complete, I need not take MCN for some reasons. Okay. So, I can make approximation in the basis, I can make approximations in the number of determinants. But if you have a complete basis and within that if you take all determinants, then this method is called full CI, and I think it is obvious now. Full means you have taken all possible determinants in a complete basis, and then the full CI, of course, in a complete basis is exact. I repeat it, that full CI in a complete basis is exact. This is an exact wave function because now there is no more error. Yes, basis. So, normal, that is the problem. So, complete basis can never be done because it is infinite. So, this is really a statement which has no meaning, not relevant, because I really can't do it, an infinite dimensional problem. However, what is normally practiced is a finite basis. This is a normal practice, finite basis, and then I can take all determinants within the finite basis, right, and then this is still called full CI in this basis, in the finite basis. The name full CI just means that all determinants have been taken. So, as long as you are taking all determinants in a given basis, we will call it full CI, because anyway in complete basis we will never get. So, we will worry about full CI in the finite basis. So, whenever we call full CI, you have to specify the basis. So, even full CI results are different. Remember, if I do a problem of Schrodinger equation solution full CI, the results will be different because your basis is different, right. If you keep on increasing your basis, your number of determinants are more in the full CI, and then the results will be different. Of course, if you do not take all determinants, then again results will be different. So, there are lots of approximations we can do, but let us understand that the exact is full CI in a complete basis. So, I have complete basis, I have all determinants, do full CI, that is an exact function. Yes. Well, usually it is infinity. So, you can't, that is what I am saying, it is in practice never implemented. That is a different matter. Limit is when you do not find results changing, you call it as almost saturated. So, that is all, that is a different matter. Mathematically maybe the number is changing, but it is changing so small that you do not care. So, you say that it is a complete basis set limit, okay, but there is nothing called complete basis set. Limit is different from complete basis set. Yeah. CBS limit is of course there, that people have found out by calculations. So, we will see that how to do the calculation, we will see later, and the energy does not change. So, that will be on Hartree-Fock also, full CI, everything, any CI calculation, but right now we do not want to discuss CI. I just thought I will tell you the form, that a form of an exact wave function is possible. That is what I wanted to tell you. If for an interacting Hamiltonian. For a non-interacting Hamiltonian, of course, any one of these determinant is an exact function. Any one of the determinant is an exact function. Question is which is ground state, which is excited state. That is a different matter. So, whichever has the lowest energy, that can be also seen from the energy of those orbitals. So, one can find out. Now, what is important is that once you have understood that the interacting problem is a linear combination of determinants, then we have to worry about how do I make good approximation. So, what is a good approximation is always to take a good basis. Even though it is finite, it is a good basis. It includes most of the physical effects of the complete basis, and I can't take all determinants also in many cases. So, I must take determinants which are physically important. So, two levels of approximations that we will do in CI later for interacting problem is that one is the basis, another is the number of determinants. So, the approximations that we will bring in CI is A, the basis. So, what is a good basis? So, what do you mean by good basis? Good basis means with a less number of functions, I should be able to generate the effects of the complete basis as good as possible. So, that is where you have to be very good. So, a lot of people have worked on this basis. This basis is not only a problem on CI, all across quantum chemistry, because this is a very, very important problem. Second is within this basis, which determinants are important. So, if we know these, we will only take those important determinants, because eventually we can't do exact calculation, we will do approximate calculation. So, we want to take physically important determinants and not MCN, because some of them may not really be important. So, these are the two very important parts which will define my CI. Okay. Even before that, there is a very important question, that we understand the value of a single determinant. I told you chemistry comes in single determinant, because if it is single determinant, chemists are very happy. You have n electron, n spin orbital. Chemists do not understand all the CI, they get confused, right? Kaiwan, same confusion will happen with electron coordinate, spin orbital. What is happening? You tell me which electron is in which spin orbital. You have to give one answer. Such an answer is not possible, but you have to satisfy an experimentalist, right? I mean, even if you say electrons are indistinguishable, okay, tell me n spin orbitals, n electrons. For an electron problem, give me n spin orbital. So, given everything, when I am saying which determinant is important, the approximation to one very important approximation that we want to do is that can I get one determinant, which is very important. One means single. Whenever I am saying determinant, please remember it is Slater determinant, which is most important among the single determinant. I can have many single determinant, but can I get one of this determinant which is the most important, because then at least I can go to the chemist with that determinant, not MCN, not even a partial set of determinant, just one. So, that is the answer that we will get from by Hartree and Fock. So, this is the answer that we will get, and that will be called Hartree-Fock approximation, where we are actually going to zero in only one determinant and not any set of combination of determinants, which is the most important. So, that is the question that I am asking, simply because after doing all this mathematics, we have to be as simple as possible. So, before we do better, let us go back to the basics and ask the question, just like in non-interacting Hamiltonian, we had one determinant which was exact. In this case, of course, we can't get anything exact, but can I get one determinant which is as close to exact as possible? I hope you understand the question. Of course, it is not exact. So when I say most important, it must be as close to the exact as possible. So this answer is given by Hartree-Fock method. So I just kind of telling before we start the Hartree-Fock, there are a lot of background work I have to do, but I just want to tell physically what is the question that you are asking. It's very important to ask the question. For an interacting Hamiltonian, this is never going to be exact, but we are only trying to ask a question, can I get a function, can I get a determinant which is as close, one determinant which is as close to exact as possible, because then I will have a very simple chemist interpretation, n electron, n spin orbitals. Okay. So the problem is that for an interacting Hamiltonian, which is sum over h of I, note again, when I write interacting Hamiltonian, please remember very simple form. I want to get one determinant which is as close to exact as possible. Of course, you can immediately say, forget about this, make it a non-interacting problem, and then I will get one determinant. The question is it as close to exact as possible? That I don't know. That is certainly one determinant I can easily get by completely neglecting it, but that may not be the best determinant, because we have no a priori reason to think that is the best determinant. So how do I get that determinant will be the content of the Hartree-Fock method. So before I start Hartree-Fock, I just thought I will tell you, I will again come back tomorrow and talk about it. I think once the problem statement is clear, what are you doing? Because many people after doing Hartree-Fock not sure what are they doing. Why did they do it? That is very important. I think I first want all of you to understand what are we doing. Technical details, if you don't miss, that's okay. I don't care. But you must know what are you doing. What is the question that you are asking? So the question that I am asking is to give a chemist one single determinant, even for an interacting problem. And would it be that determinant by simply neglecting this? Then I have an answer. The answer is actually no. So that is the reason Hartree and Fock did. That's an answer that I can tell before I do it. Okay. So I think we'll start with that Hartree-Fock method now. But before that, there is certain background work that I have to do. Some little bit of mathematics, which is essentially calculating matrix elements of the Hamiltonian. I will have some rules, letter rules. I will lay them down because they will all be required. And of course, the most important thing will be answered by what is called the variation principle. So I will again repeat the variation principle. I have done it in 4 to 5. I will repeat variation principle, some certain mathematical rules for getting the matrix elements before I actually can tackle this question. So some background work will be done from tomorrow. Okay. So but I hope you have understood the question. I think if you have any problem with the question, please ask. You know, that is most important. In fact, CI is much more easy. It is just mathematics. Hartree-Fock is more difficult because it has a physics. How do I get the most important? So there is a physics built in, and if you don't ask that question, then you will miss the essence of the Hartree-Fock. So Hartree-Fock will be eventually very good, yet not good enough, because it is still a single determinant. So then the question that we will ask, how good it is, why is it not good enough, that we have to do something better. In fact, the Hartree-Fock was developed in 1933. Hartree and Fock did long back. Why didn't quantum chemistry stop there? You know, that's the question. So obviously it is not good enough. So all those questions we'll ask later, not today. We'll first see how can I do a best single determinant picture, and then we'll see how can I improve this. On the quantum mechanics, the first paper came in, Hitler and London did valence bond theory in 1927. Then Hartree and Fock did in the 30s. This is molecular orbital theory. Okay, I think things will become more interesting as you go to the real part. So please try to follow and make sure that you ask questions. Okay, I mean, he asked a question, good question. Everything was good question. I mean, everybody was confused the way you said, because everybody will think just change 1 and 2 index, but it is not that. It is a coordinate change. So it was a good question, I would say. So please feel free to ask questions. That's very important. No, 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 it is a good question. I mean, I don't say anything which is a bad question. Okay? Okay. Thank you.